Hello, welcome to my presentation. I'm Sasan Asadiabadi, and today I'm going to present our work, Vocal Tract Landmark Tracking in Real-Time MRI, which is accepted for poster presentation in ICASSP 2020. I'll briefly introduce the problem we are targeting in this work and give some of its applications. Then I will explain the methods we introduce in details. Finally, I will present the experimental results and conclusions. The problem we are targeting in this work is detection of vocal tract contours in real-time MRI sequences. We are targeting a tracker which is fully automatic and subject independent. A vocal tract contour is defined as a set of landmarks on its boundary which separate the tissue from the cavity. Vocal tract consists of several articulators which are jointly involved in sound production during speech. The main application of the vocal tract contour tracking is studying the basis of human speech production system. There exist several other applications such as articulatory synthesis and studying sound disorders. This task is classified as the formable contour tracking problem, which in our case is challenging due to the complex anatomy of the vocal tract. Some of the articulators such as tongue and velum are highly and rapidly deforming during speech, which makes them hard to detect and track. On the other hand, low spatial and temporal resolution and lack of intensity variation in the real-time MRI images makes these problems even more challenging. Now I will explain in details the method we propose in this work to solve the vocal tract contour tracking problem. In this work, we describe each landmark with two parameters: the location, which is the XY coordinate of each landmark in the image, and a label which describes which region in the vocal tract each landmark belongs to. We define a vocal tract contour as 80 landmarks on its lower and upper profile, which span the tract from the glottis to the lips. To study the time-varying shapes of the vocal tract in speech production systems, it is important to locate the movements of various articulators separately. Therefore, we consider 7 regions on the tract to represent different articulators, which are highlighted in different colors in this figure. The main idea in here is utilizing heat map regression to estimate a sequence of heat maps which are associated with landmark coordinates for each MRI frame. A heat map is a sparse image which encodes the information in the neighborhood of each landmark and has the same resolution of an MRI frame. We utilize deep learning to train a network which is capable of estimating these heat maps and their articulatory class labels as well. After training the network, the vocal tract landmarks are recovered from the heat maps in the heat map to landmark stage, or what we call in here as H12 block. The landmarks are then stabilized in space and time using a spatiotemporal stabilization scheme for a more accurate vocal tract contour detection. We use a fully convolutional network to estimate the heat maps and their labels. The target heat maps are generated using a Gaussian kernel and estimated at the regression part of the network. The FCN also contains a classifier which is trained to predict the landmark labels, which are a one-hot vector representation of classes. The input to the FCN is a fixed resolution MRI frame of size 128 by 128. Here we have the block diagram of the trained single input, multiple output FCN. The FCN performs a regression and classification in parallel. The regression and classification networks share weights at the convolutional block layers. A number of convolutional layers perform as a feature extractor at the early stage of the FCN. The output of these convolutional blocks is then fed to a sequence of softmax layers for label classification and to upsampling and adding layers for the heat map regression. We train the network to minimize a combined MSE loss for regression and cross-entropy loss for the classification using the Adam optimizer. Upon a successful training of the network, the stack of heat maps are estimated at the regressor output, and a sequence of class labels are predicted at the classifier's output. As given in this figure, regions with higher values in a heat map indicate a landmark presence. To recover the landmark locations from the heat maps, we use a weighted combination of the top K maximum heat map values, where K is a hyperparameter which needs to be tuned. For the classifier's output, the class labels at the boundaries separating different articulator regions may not be very smooth. Therefore, we use a medium filter of size 5 to filter the noisy boundary decisions. There are two major drawbacks in the proposed landmark tracking system. First, the heat map regression ignores the strong spatial correlation which exists between the neighboring landmarks. Second, the counter estimation is executed separately for each MRI frame, which is ignoring the temporal coherency of the articulatory movements. To overcome these two problems, we propose a spatiotemporal stabilization scheme to further improve the accuracy of contour tracking. Using PCA, we generate a statistical shape model for the vocal tract and represent each vocal tract contour with the parameter in the PCA space. Using Kalman filters and parameter value restrictions, we perform the landmark stabilization in space and time. The vocal tract shape model is generated using PCA over a training set. The shape model is described as the mean contour shape and eigenvalues and eigenvectors of the contour shape covariance matrix. PCA projects the highly correlated contour space to an uncorrelated and lower dimensional parameter space. We consider 12 parameters coming from the 12 eigenvectors corresponding to the 12 largest eigenvalues, which is enough to explain 95% of the variation in the training set. Each contour can be projected and reconstructed from the 12 PCA parameters. In the spatial stabilization scheme, the PCA parameters corresponding to the estimated contours are restricted to a range to allow only plausible contour shape. This way, the outliers which can arise due to independent estimation of the landmarks will be removed. The temporal stabilization is performed using Kalman filters and the PCA parameters. PCA parameters and their velocity of change from one frame to another form a Kalman state. PCA parameters are stabilized using the estimated values at the MRI frame and the stabilized value in the previous frame. The diagram of the spatiotemporal stabilization is given in this figure. Each estimated contour from the FCN and H2L blocks is first projected to the PCA space using the shape model. First, the temporal stabilization is executed. The Kalman filter has two stages, prediction stage and correction stage. In the prediction stage, the state value for the current frame is predicted using the previous stabilized value. Then, using the current observed value and the predicted value from the prediction stage, the Kalman state is corrected and stabilized. After temporal stabilization of a parameter, its values is clipped to the defined range in spatial stabilization to remove outliers. Finally, vocal tract contours are recovered from the shape parameters. We described the proposed vocal tract contour tracking scheme for the real-time MRI. Now we will give the experimental results. To train our networks, we utilize the USDTMIT database, which contains MRI videos of 10 subjects. The spatial resolution of the video frames in this dataset is 68 by 68, which needs to be scaled to the FCN input size. Our networks are trained using the Keras deep learning library with TensorFlow backend and an NVIDIA GPU, and tested using OpenCV DNN module and an Intel Core i7 CPU. We performed experiments in a leave one subject out cross-validation. We only used 3 speakers from the USDTMIT database, which have the ground-labeled contour data. At each cross-validation, we train the network with 2 speakers and test the performance on the third left-out speaker. We consider mean sum of distance, which is a point to closest point error metric for the spatial estimation error, and the landmark temporal stability error as the temporal estimation error metric. Other than the FCN architecture, the main important tunable parameters are sigma, which is the variance of Gaussian kernel in heat map regression, and k, which is the number of top maximum values in H12 block. These parameters are tuned using a greedy search over a specific range. We compare our method with two of the recent methods in the literature, DLIP, which is originally a facial landmark detection library and recently used in a paper for the vocal tract landmark detection, and MLR, which utilizes a linear regression to map a PCA representation of MRI frames to a PCA representation of the vocal tract contours. Given in this table, objective evaluations indicate that the proposed approach outperforms the baselines both in terms of spatial and the temporal error metrics. We also compare the results of the proposed FCN with the stabilized FCN and observe that the spatiotemporal stabilization scheme helps to improve the quality of contour tracking. Regarding the speed, the proposed method can run around 9 FPS on a GPU and, despite the deep network, around 2 FPS on a CPU. Here are some examples of the estimated vocal tract articulators using the proposed method. It is observed that the method accurately detects the vocal tract contours for all defined regions and for different configurations of the vocal tract shape. Some video examples of the contour tracking can be found on my webpage. Just feel free to click the link and play the videos if you're interested. So in conclusion, we presented a robust subject-independent vocal tract contour tracking in real-time MRI. Vocal tract landmark locations and labels are detected via heat map regression utilizing a fully convolutional network. A spatiotemporal stabilization scheme was introduced to model the spatial and temporal correlation in the articulatory movement. For future work, we plan on optimizing the proposed network for more accurate vocal tract contour detection. Our major plan is to come up with a smart way to properly integrate the H2L and stabilization scheme into the FCN for an end-to-end vocal tract landmark tracking system. Here are some references. Thank you very much for your listening. If my research interests you and you have any questions regarding this paper, feel free to contact me via my email.